Imagine a thin shell of invisible shrapnel enveloping our world. This is not the opening scene of a science fiction film. It is a description of a real and growing problem in low Earth orbit. Millions of pieces of debris circle our planet. They are the remnants of over 60 years of space exploration, ranging from spent rocket stages to tiny flecks of paint. A small screw moving at orbital velocity carries the kinetic energy of a bowling ball dropped from a skyscraper. When these objects collide with active satellites, they can cause catastrophic failures. This scenario has a name: the Kessler syndrome. Before we venture further, let us outline the path ahead. Think of it as a 30-second roadmap to a complex problem. First, we establish a baseline, what low Earth orbit is and why it matters. Next, the first-order consequences. Immediate service disruptions as satellites begin to fail. Then, second-order effects. How those losses propagate through finance, transport, energy, and safety. Finally, escalation and the long-term altered state. Recovery grows difficult. Access to orbit narrows. Societies adapt on the ground. This is a sober look at cause and effect. Physics first, payoffs later, and an open question at the end. Low Earth orbit, or LEO, spans roughly 160 to 2,000 kilometers above Earth, our most accessible rung into space. Its proximity keeps costs lower. Satellites here circle the planet in about 90 minutes. That speed and altitude make LEO ideal for communications, observation, and services we use every day. Large constellations deliver internet, connect remote communities, and backstop terrestrial networks. LEO hosts Earth observation platforms for urban planning, agriculture, disaster response, and climate monitoring. Precise timing signals from space synchronize stock exchanges, coordinate power grids, and enable cellular networks. The International Space Station traverses this region, enabling research impossible to replicate on Earth. In 2026, reliance is rising, and so is congestion. Launch costs have fallen, object counts have surged, thousands launched in recent years, with tens of thousands planned. Every launch, deployment, and mission compounds the traffic management problem. This delicate, crowded environment is what a debris cascade threatens to destroy. If this analysis is valuable, tap like to help others find it. Comment with the service you rely on daily. Subscribe for more mechanism-first explorations from IFRS. A cascade would not begin with a global announcement. It starts with scattered technical failures. First-order consequences are direct. Satellites are struck and fail. Service becomes patchy or disappears for specific regions. A communications company reports the loss of a key asset. Traffic is rerouted until more failures open wider, more permanent gaps. The promise of ubiquitous global internet begins to fray. Navigation degrades. Phones struggle to lock, aircraft flag unreliable signals. Crews fall back to ground-based aids, safer but less precise. Fleet tracking goes intermittent. Precision is the first casualty. Small delays and extra fuel burn scale across millions of trips, creating real costs. Next, our eyes on the planet begin to close. Forecasts lose certainty. Warnings become later or broader. Farmers lose vital imagery, revert to less efficient methods, lower yields, wasted resources. The ISS faces unprecedented threat. Avoidance maneuvers become constant, then impossible. Experiments end abruptly across materials science, medicine, and fundamental physics. The initial phase is one of loss. Second-order effects are systemic and more dangerous. High-frequency trading depends on atomic clock timing. Lose it and nanosecond precision vanishes. Markets slow, liquidity dries up, and the risk of flash crashes increases. Transport is not a single ship. It is an interlocked chain that fails without precise positioning. Ports slow, trucks wait, just-in-time collapses. Shelves begin to empty. Fiber carries the bulk, but satellites balance loads and reach the remote. Remove them, and congestion spreads. Digital traffic jams form. Internet speeds drop for everyone. Remote communities lose basic communications, telemedicine, and online education. Public safety suffers. Response times lengthen. Managing wildfires and quakes grows harder. Militaries are partially blinded. Early warning and treaty monitoring degrade. The dominoes have begun to fall, and they knock into everything. The engine of Kessler is feedback. Debris creates more debris. A single breakup can generate thousands of new projectiles. As fragments multiply, the probability of future collisions climbs exponentially. The environment shifts from degraded to actively hostile. Recovery attempts face rising risk and dwindling windows. Insurance costs skyrocket. Some carriers exit the market. Without insurance, launches slow to a trickle, then stop. Networks lose redundancy, ensuring eventual failure of internet, weather data, and navigation. Even cleanup missions risk adding to the problem. Orbital gridlock. Actors hoard what remains. Accusations rise. The tragedy of the commons plays out in orbit. After the cascade stabilizes, humanity settles into a long-term reality. Leo becomes a treacherous junkyard, not empty, but unusable. Access grows rare and expensive, reserved for critical, hardened missions. For practical purposes, near space is off-limits for decades, perhaps longer. Life adapts, but becomes less connected, less efficient, and less informed. Economies are reshaped. Societies invest in ground infrastructure to compensate. Stratospheric platforms mimic some satellite functions, regional comms and observation, but they lack global reach, persistence, and the unique vantage of space. A generation of research is lost. Earth science is hobbled without routine orbital data. Even journeys to the Moon or Mars require first passing safely through LEO. A broken sky becomes a permanent reminder of a frontier we reached, polluted, and lost. We have explored a future governed by physics and system dynamics. A chain reaction can unravel the technological fabric of our world. This outcome is not inevitable, but it is a distinct possibility on our current trajectory. Treat orbit as limitless, and we roll the dice, hoping the tipping point is farther away than models predict. Alternatively, active stewardship, deorbit standards, cleanup missions, and real space traffic management. It requires investment, collaboration, and foresight. Space must be treated not as a wild frontier, but as a fragile ecosystem to be protected. Which path will we take then? Add your voice, like, comment, and subscribe to keep these evidence-driven stories alive. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.